So now we're going to review the second concept. We have free energy. So remember, free energy is what we represent with this term delta G. So before answering these first two questions, I want to remind you of what delta G, what we use it for. What we tend to use free energy for is to help us predict whether a reaction is going to be spontaneous or not. So, as a reminder, first off, you can find the value of delta G by combining our values for delta H minus T times delta S. So combining enthalpy, which is that concept you studied in 1211, and now entropy from 1212, along with the temperature, we can find a value for this. And when we get that, we have some conditions. One possibility is you get delta G equals 0. That means you are exactly at equilibrium even under standard conditions. Note, you usually won't get exactly 0, but that would be what that would represent. So if delta G were less than 0, that means that we're going to have a negative value for it. And that's going to give us a reaction which is spontaneous when we're working with it. So, I lost my thing. So our spontaneous reaction is going to head towards equilibrium, as written. Now, if you get delta G is greater than 0, that means the reaction is written as non-spontaneous. So under standard conditions, remember that's the 1 molar of your concentration for your aqueous, 1 atmosphere for your gases, that as written, it's not going to go forward like that. It's actually going to go in the reverse direction, as written, if it were to do that. Without putting energy in, the reaction's not going to happen. The other thing to note is, just like with entropy, you can look up values for delta G for a chemical reaction and add them all together to get a value. So I'm not going to do another example that it's solved just like the entropy one in the previous video you should have just watched. You just look up G's instead of S's. You're still products minus reactants, you're still accounting for the moles. It's done exactly the same way. Just like in 1211, you did that with enthalpy. Same idea. Now, let's answer some questions with that. If you haven't tried these yet, try the 2 questions I have on the screen, and we'll go over them in just a second. Okay. First question, which of these will result in a reaction which is spontaneous? So let's consider the equation we had. All right. That delta G was equal to delta H minus T delta S. So if we want it to be spontaneous, we want delta G to be negative. And we want it to be at all temperatures. So the way to get that is we want this term over here to be negative. And because as it's negative, pretend like you were at 0 Kelvin. We can't get there. But if you were at the lowest temperature possible, T delta S goes away. Since T would be 0, 0 times that, that's 0. So then your enthalpy would be the only thing that mattered. So if it was negative, it would definitely be spontaneous. That covers at least some of the temperatures. The issue is that T delta S, if it ever gets enough to become so positive that it overwhelms the enthalpy, then delta G overall will be positive. So in that case, to make it so that at all temperatures were spontaneous, we also need to get the second term to be overall negative. So for it to be overall negative, we want delta S to be positive, since you already have this minus sign here. So if you're subtracting a positive, then it's going to make delta G more negative. Note that temperature, we're always working with positive temperatures, so we don't have to worry about what happens if the temperature were negative 30 Kelvin, because we can't do that, and so we're not worried about that. So that means that the negative case here and the positive case for delta S would be all spontaneous for that. You will please note that if the signs on delta H and delta S are opposite from each other, it's always either all spontaneous or never spontaneous. When the signs are the same, so that would be like answers A and C, it's going to be sometimes spontaneous and sometimes not. To work with those, you've got to find out where delta G would be 0, and you can solve for the temperature for that. And then you can use that to figure out whether it's going to where it's going to be spontaneous and where it's not. Now, our second question, what is delta G given these values? So this is a common thing you get asked to do. You could also have to look up your delta H and delta S values. So we have our equation, delta G equals delta H minus T delta S. So I'm going to plug those values in. So first delta G is 84.2 kilojoules. Now minus, our temperature is 25 degrees Celsius, so we convert that to Kelvin. So we have 298.15 Kelvin. And then we get to the delta H, or the delta S, sorry. An important thing here, which can be easy to not notice if you haven't been paying attention to your units and problems, because as a professor, we tell you all the time, but I recognize as students, and I'm sure like, okay, look, I just put these numbers in and it gives me an answer, and I write the unit because I memorized it. But what you need to notice here is this unit for S doesn't match our unit for H. So in general, when you look up entropy values, they are usually in joules. Our enthalpy values are usually in kilojoules. I forgot my J. If you want to add these two things together, they need to be the same. So to do this problem, I would either need to convert the enthalpy to joules, or what I'm going to do is convert this entropy into kilojoules. So joules to kilojoules means I have to divide by 1,000. Since a kilojoule is a larger unit than a joule, I have fewer kilojoules than I have joules. So when I do that, I'm going to get negative 0.0923 joules per Kelvin. And then the kelvins will cancel, and I'll be left with kilojoules. Sorry, I meant to say the word kilojoules because we divided by 1,000. So we'll be left with kilojoules and kilojoules. When you combine those together, you'll get that in that same unit. So we have delta G equals, when I combine those two, I'll get 112 kilojoules. So that's the first part of the question. It asked me for what was the delta G. The second part is this reaction spontaneous? Well, delta G is positive, so no, this reaction is non-spontaneous. You could also note that if it only asked for spontaneity, you could have looked at the signs of these. And since delta H is positive and delta S is negative, that's true that for all temperatures it's non-spontaneous, so you wouldn't actually have to do the math. On the other hand, if delta H had been negative and delta S had been negative, since they're different signs, you would have actually had to do the math because that will sometimes be spontaneous and sometimes not. So that's some calculations using that. So I also want to go now and do some review of Hess's law. So I'm going to start with a hopefully straightforward question. As a reminder, this is done just like when you did in 1211, your intro general chemistries, your first semester, with delta H. So I want you to give this a try. Okay, here we look at the changes, and if we compare the top to the bottom equation, what we notice is we have doubled all of our values, and we flipped our direction of our reaction, which means we have to change our sign. So if we multiply this times 2 and flip it, we will get exactly 4NH3 gas on the reactant side goes to 2N2 and 6H2. So when you do that, you change, the flip changes the sign, so now we're positive instead of negative, and we have now doubled it, and when we double it, we will get a value of 65.92 kilojoules. So this is how we do it with a single equation. Most times you're going to be combining multiples, but we have to use this base idea to do that. So let's look at a second example. I want you to give this a try. Okay, hopefully you've tried this out. So what we need to do is figure out how to combine equations 1, 2, and 3 to get this top equation. So I'm going to start by looking at things where they're the most similar and what I can change. What I notice right off is nitrogen dioxide only shows up in equation 3 down below, and it's a product. And here it's a product, in both places it's 1. Therefore, we're going to keep this exactly the same. We're not going to make any changes to equation 3 because they're identical. And there's no other NO2s in any of the other reactions. So if I want to get the top reaction, I have to leave the bottom reaction alone. And that's nice. We don't have to change anything. Second, I'll look at that also fixes the nitrogen monoxide as well. So that one's by itself, and that one's by itself. Next, I've got to get an oxygen. And I only want one of them, and I want them to be a reactant. So in equation 2, it's a product. So here, I'm going to have to multiply 1/2, or divide by 2, and I'm going to have to flip it. When I do that, I'm going to change equation 2 so that now it is flipped. So it starts with an oxygen gas molecule, forms half of an oxygen gas, and that's going to have a delta G value. So we flipped it, so now it's negative, and we've multiplied by 1/2. So now it says a value of negative 231.7 kilojoules. Note we've created all three things, but you'll notice if you try to add these three equations together now, you have some extra molecules. In particular, we have to deal with the oxygens. Currently, as written, the oxygens won't cancel because we have half an oxygen in the products, we have one oxygen in the products here, and we have three halves oxygens in the products here. So those all add together to give you oxygens, but there shouldn't be any extra oxygen O2 molecules at the end. You'll also notice that you have one ozone molecule in equation 3 as a reactant, and you have one ozone molecule in equation 1 as a reactant. So to get rid of the ozone, and also this will fix our oxygens as well, we're also going to flip equation 1. So equation 1, did not mean to do that, there we go. Equation 1 is going to become 3/2 oxygen gas goes to O3 gas. And that's going to give us a delta G, not of reaction, equal to, we now have negative 244.8 kilojoules because we flipped it. Now I'm going to rewrite equation 3 here so we can add them together. We didn't change it, but let's just write it here. So we have NO plus O3 reacts to form NO2 plus O2 gas. And let's see if we've done enough to now balance our equation so that we only have the 3 things we expect in our final reaction. So first we can see our O3 here is a product and our O3 here is a reactant. So they cancel. On the reactant side, we have 3 halves of an oxygen. On the product side, we have half an oxygen and 1 oxygen. So 1 oxygen plus half an oxygen gives us 3 halves oxygen, and those can cancel with the 3 halves oxygens here. So then we can add our reactions together, and the remaining elements, we have an oxygen gas plus a nitrogen monoxide gas reacts to form NO2 gas. So that gives us our reaction, which means we can then just add our delta G's together. And I didn't rewrite it, but I'll go ahead and do that this was negative 199.5 kilojoules. So now, since they can add together, we can just add these 3 values together. And if you do that, you're going to get a value of negative 676 kilojoules. Okay. So that will finish up with our review on Hess's law and the free energy portion of our thermodynamics chapter.